So the next speaker is Akira Takahashi. He will talk about the brave new world of global generic groups and UC secure ZO snarks.
Thank you for the introduction. So this is a joint work with Jan Bobot, Puya Fashim, and Mark Kovacs. And I would like to thank Jan for making all the slides. So he has a bunch of nice characters inspired by Scottish Highland cows. So you will see a lot of those soon. Okay, so this is a proof system sessions. I'm not going to repeat zero knowledge and the proof of knowledge. But here, essentially what we need to make sure is that we have some superpower that malicious provers or verifiers don't have. For example, if you want to have some proof of knowledge, then of course the extractor has to have some superpower, and the malicious verifier should not be able to invoke the extractor, otherwise it breaks the zero knowledge. So let's keep this in mind. And the goal of this work is to prove the UC security of some ZK snarks. So typically, in order to prove UC security, you first need some combined notion called simulation extractability. So essentially, this allows an adversary to have some access to a simulation oracle, and then basically the extraction should succeed even after the adversary observes many simulated queries. So this essentially models the situation where the adversary has observed many proofs generated by other parties. And essentially this makes sure that the proof system is also non-malleable. The adversary is not able to mold the existing proofs to construct the proof without knowing the witness itself. So however, there's still a gap. So in order to achieve the UC security, you need a slightly stronger property. So one property is straight line knowledge extraction. So this means that first, you cannot, for example, rewind adversely to extract the witness. There has to be some stronger way to extract the witness. So this is why there are many previous papers that proposed generic compilers, turning NISC with the standalone proof of security into the one with the UC security. However, unfortunately, these compilers inevitably incur some overhead in the proof size or the approval time, except the one work, which was presented by Giacomo just now. So this was a very nice work. Basically, they observed that there are some already straight-line extractable ZK snarks, which are purely hash-based. In this case, you can already conclude that these schemes are already UC secure. So our work is somewhat complementary. So there are other ZK snarks that are not completely based on hash. We have a lot of group-based snarks. So our question is whether we can design a group-based idealized model allowing for UC secure ZK snarks without modifications or overhead. So before presenting our version of idealized model, I would like to briefly recap how we treat the random oracle in the UC setting. We take a lot of inspiration from these works. So the straightforward way to model a random oracle in the UC setting is to, of course, define it as an ideal functionality, local to each session. So basically, you can just define some random oracle ideal functionality, which can be accessed by parties in the session. And in this way, for example, to prove some proof system is UC secure, UC realizing FNISC, then the simulation is relatively straightforward. There's an ideal adversary who has full control over the random oracle. Is this a good model? So actually, the previous work pointed out that this is not a very good model. So let's see why. So for instance, now let's consider there are two sessions relying on the random oracle. So if you treat the random oracle as a local functionality, basically what happens is that each session has an independent and fresh instance of the random oracle. So we face a weird situation. For example, if both protocol sessions make query to the random oracle, because random oracle instances are different, they might output a different output, even though the inputs are the same. So this doesn't properly model the real-world situation where the same hash function is used by different protocols. For example, in practice, we use the standardized SHA-2 or SHA-3 across many different protocols. So can we circumvent this weird situation? So there are a few nice previous works which basically treat the random oracle as a global resource. So our work is also inspired by the modeling strategy of these works. So they basically define the superpower in such a way that the same random oracle instance can be accessed by different protocol sessions. So now we define the random oracle as a global functionality, and all these parties can access the same instance of the random oracle. So this is how we can model how the same hash function is used in practice. And to make this useful for UC realizing FNISC to prove the UC security of NISC, we need some additional property. For example, like I said, extractor needs some superpower, which is, for example, achieved by observability of the random oracle queries. However, if you treat the random oracle as a global resource, then the random oracle is external to the extractor. So this is why you need some observability mechanism. And in the case of random oracle, this can be achieved by domain separation. So basically, you include a prefix with a session ID. And if the caller session ID doesn't match the prefix, then you consider it an illegal query. So this is how we achieve observability. So now let's move on to the group-based idealized model. So in this work, we define a global version of the generic group oracle. So what was the generic group model? So essentially, the goal of the generic group model is to treat an idealized group with no extra structure from the perspective of the adversary. So basically, the adversary in the GGM only obtains random encodings of the group elements, and they're only allowed to perform generic operations on these random encodings, and then they obtain the resulting encoding of the group element. And this is very strong, and it's also very useful for proving the security of non-interactive zero-knowledge proof. Basically, in the GGM, the extractor can observe all the generic group operation queries, and from those queries, the extractor can recover the secret witness. So to be a bit more precise, in the GGM, we define some generic group oracle which accepts operation query, and then the operation query comes from some random encodings, and then the oracle performs generic operations internally, and then it outputs the random encoding of the corresponding the output group element. So once you define a generic group, and we can sort of replicate the approach from the generic random oracle, the global random oracle model. So in a similar fashion, we can define a strict version of global generic group oracle. Now we treat the generic group oracle as a global resource, and this can be accessed by different protocol sessions. So in this way, we model the situation where the same group parameters are reused by different protocols, some standardized curve in the case of elliptic curve-based crypto systems. However, this is not sufficient. So this strict version of generic group oracle is not very useful for proving the security of NISC, because again, the knowledge extractor needs to observe group operation queries. So we need to implement some observability mechanism for the extractor to obtain relevant information so that they can extract the witness. So how can we design that? So just to briefly recap how extractor works in practice, let's take a famous Gross-16 proof system as an example. So in this case, basically the adversary performs group generic operations on the CRS group elements, and then just by observing those group operations, the extractor can recover the corresponding wire value associated with the relation. And this wire value essentially corresponds to the witness. So the extractor really needs to obtain the information about those generic queries with respect to the CRS or input group elements. So in order to, when designing observability of the generic group, we faced several technical challenges. So basically, we have a set of somewhat contradictory requirements. First of all, we need to make sure that a simulator and the extractor really see group operations made by the environment, because if you treat the functionality as a global resource, environment can also make query to the global oracle. So this is important for extraction, but at the same time, not everything should be observable, because environment might also take advantage of the observation mechanism. So this means that, for example, if the simulator performs some simulation queries using the global generic group oracle, the environment might notice the difference between the real world and ideal world. So we have to make sure that the environment doesn't see some secret operations performed by the simulator. So this initially seemed impossible, but basically we got inspired by the global random oracle approach. And essentially here we also implement some form of observability using domain separation. But the way to do domain separation is very different from the global random oracle. So here's the intuition. So we introduced the following observation rules. Basically, each generator obtains a fresh, each session obtains a fresh generator, and then the parties are only allowed to perform generic operations on these session-specific generators. Otherwise, the queries become observable. I'm going to quickly go over what the actual functionality looks like. So basically, the functionality does some sort of bookkeeping using polynomials, and each polynomial variable is associated with fresh group generator. And as soon as parties make mixed operations using different group generators from different sessions, then this becomes observable. So that's the high-level idea of the functionality. And in the actual functionality, we also implement pairing operations, oblivious sampling, and we also allow multiple generators per session. And for the complete protocol, please refer to the paper. Just to recap what the random oracle and the GGM in the UC look like. So basically, the local versions are not very useful because it doesn't model the sharing of the same resource in practice. So that's why we introduced a global version. And once we have global version, we need the domain separation to implement observability. So that's the idea. Okay, so I'm running out of time. And what I want to say here is that we, as a case study, we analyzed Gross 16 in the UC in the presence of a global generic group. Okay, so just to conclude, we had a new design of global generic group model, and we faced many technical challenges when designing the observability. And also, there's a closely related work for AGM, but our approach is actually very different. Essentially, we don't modify the UC framework. Instead, we introduce the global functionality to model this situation. So that's it from me. I'm happy to take questions.
Any quick questions?
Thank you for the talk. So I have a question. Does this also extend to the algebraic group model? Can you comment?
Yeah, so we think this is very orthogonal to AGM because, as I said, like basically we need the global functionality that performs group operation. But in the AGM, this task is sort of delegated to the adversely and the environment. So environment is responsible for coming up with representation. But this one is a bit different, I think.
Wouldn't it be the simulator that has to be algebraic?
So that's not the requirement, but when you prove the security of some protocol, yes, the simulator often behaves like an algebraic algorithm. They also need to...
No, I mean during composition, right? I mean, you have to... Okay, maybe we can
maybe we take it offline.
So.